Let's talk about other kind of telescope. So according to your study guide or IB syllabus, we of course talk about a few optical instruments, including microscope and refracting telescope in the previous video. So let's take a look of what you need to know as well. So we will go through something called reflecting telescope, and then there are actually 4 more kinds of telescope in total. So including reflecting telescope. There's also called the radio telescope, which looks like a single dish. Usually you see in the rooftop of some building, especially the old buildings. And there's also another kind called the radio interferometry telescope. So that actually means it's basically a lot of single dish radio telescope, but we'll explain why. The last kind is called the satellite borne telescope, and yeah, these 4. And if you try to look at the study guide, I can also put the link in the description for your reference. Other than that, for application and skill, we also of course learn about microscope, refracting telescope, and then I think, yeah, that's also telescope. Also, okay, these are all we talked about in the previous video. And so here is one thing that you need to learn about as in terms of application and skills, is to compare the performance of the Earth-based and satellite-borne telescope, which we'll talk about that in the second half of our video. Okay, and we also have to learn the basic idea and the design to Newtonian and Cassegrain telescope. These two, Newtonian and Cassegrain mounting or telescope, is under the reflecting. Okay, this is too far. Under reflecting telescope. That means the first kind of telescope we will talk about in this video. And for the radio it's very hard to say, interferometer telescope, it would be something to do with the diameter. Later on we'll talk about it in the equation. And then yeah, will be a array of telescope simply. And there isn't any equation from the data booklet that is related to this video, but then there is actually one equation you need, and I'll explain later on. So before we start, I would want you, as usual, I want you to read the Taskbook, page 23 to 26. And I will also want you to read the quantity as well. So on quantity, you should find under C2, there is a section about telescope. So here are some diagram of different telescope, including refracting telescope, reflecting telescope, the single dish radio telescope, the array of telescope, and the satellite borne telescope. Okay, so these are the all kinds of telescope we will talk about, and it will be nice if you go through the content. Actually, I talk about refracting already, and this is Newtonian, and this is Cassegrain. So try to take a look, especially their diagram, and also there's a very nice table from Cognitive that they compare the two, so you can take a look of that as well. For radio telescope, there is very simple simulation. Actually, it's more like it's nothing you can do. It's just adjusting the angle, and then you can see the signal got reflected to this and this parabolic disc. And this is the equation that will be required. There's also a nice video about a very large, I'm not sure if it's still the largest radio telescope, which is it's just really huge. Alright, this is a telescope, so be careful that I mean, or I should say, this is a new idea for you, that in the past people, before they study physics, maybe they would think that, hey, this is telescope, and these are not telescope. Actually, these are also telescope. Alright, this is also telescope. This is not just satellite, but this is one kind of satellite that is acting as telescope. Okay, So try to read through this and come back to us. So pause the video now and read both textbook and the Cognitive. Okay, so let's talk about the difference between reflecting telescope versus refracting telescope. That means the one that we learned in the previous video. So as you can find this one, this is a nice comparison, however, in the textbook that I find. And also quite nice to consider as well. Imagine you are the engineer building telescope in the future. So reflecting telescope actually has quite a lot of advantages. Actually, it's basically if you are a professional, you would rather use reflecting telescope for observing the stars rather than refracting telescope. This picture on the right hand side is refracting, and that is the one that you use in the cam as well. So I'll explain right now. So basically, reflecting telescope, whenever, actually no matter what, whatever telescope, if you want to see distant object, it will require a very large, I shouldn't say lens, but it should be a very large aperture. So imagine like the hole, basically, for getting the light to go in, you must have a much larger area so that you can collect more light, because it's far away, and therefore the intensity is usually low, as you could experience during the camp when you're doing the stargazing. For the dimmer star, it's really hard to trace and really hard to observe, and therefore you would want to make a larger lens. The similar situation is, even if you haven't used this before, is that if you ever try to use your phone should have a camera, and so you will find out that the phone camera, the size is much smaller, and in that case it's harder to take a picture at night compared to those we so-called professional bigger camera that people holding with an actual lens, actual big lens. So the lens size basically is affecting how much light it go in. So when you try to make a large lens, the glass has to be so-called homogeneous and free of air bubbles. That means the curvature has to be very smooth, and also the material has to be very consistent. There is actually a video about how we can make optical lens, and it will be actually quite nice to watch. I will put the link in the description, and I will encourage you to take a look, basically. And actually that tell you quite a lot of manufacturing process, how we actually make it. I actually make one before, and so what you can do is you have to make a container, and then you have to pour something like this inside, and these are actually the material for making the glass. So imagine when you're pouring these, some air bubbles some air may be trapped inside, and that make the air bubbles. And so later on they will use some other chemical, actually I don't know what that is, you may want to listen to the video, and then they will become transparent. Alright, and they use the machine to polish it so that the shape is very nice, it's parabolic, yeah, and then that become the lens itself, right, like this one. So very nice video for you to watch. So since you have to make a very large lens for refracting telescope, then there is a problem, because the lens must be very heavy, and in that case, if you try to build this one like we have here, you can see there's a support right here. If this gets very heavy, then your support has to be very strong as well, and it would easily collapse in that case. So that's why for building a larger one, people usually would prefer to build a reflecting telescope, because for reflecting telescope, which you can see, I'll come back to this page, this is the Newtonian design, where you can see the lights come in this way, coming in like this way, coming in this way. This is a hole, and then the light got reflected along this mirror. This is the converging mirror. That is the concave mirror. It's like the convex lens. All right, just a quick concave mirror, and that is acting like a convex lens, and that's why we call it converging. all right, because both of these are converging the light to a certain point. And there is a plane mirror which is 45 degree towards this line. So that basically means like this is 45 degree along the principal axis, and that basically is just to relate the light in a certain degree with go for 90 degree in this case, and then that go to your eyepiece. So the basic thing is here you can see the eye looking at the image is at the side, and then that means here basically the one end of the telescope, the other end, of course this end is to getting the light to go in, and then this end you can set it on ground. Think about that, you can set this on the ground, so it will be easy to set up, because just now we talk about if it is heavy, then you apparently it cannot support its own weight. As for the second one, which is the Cassegrain designed, both of these are reflecting. Okay, be careful, both of these are reflecting. This is reflecting, Newtonian is also reflecting also. Okay, and the difference between these two is you can see that for Cassegrain there are two kind of mirror, and then I think it's quite self-explanatory. The different thing is they got other than two, they got two mirror in Cassegrain, and also the eyepiece, of course, both of them have eyepiece. It's a location where is you see here. Just now for Newtonian is at the side, right, at the side. So for this one, it's also not so easy to set up, because you cannot just set this side as the ground on the ground, because you still have to keep this side as the eyepiece. However, since both of these, or even at least Cassegrain here, this is a mirror, and of course Newtonian can set on the ground, so it's no problem, but you can see this is also a mirror. Then what you can imagine is if you try to set up a support like this, all right, you can do wherever you want, all right, for the whole mirror. So imagine this is the whole mirror, you can set up the support for the whole thing everywhere, even in the middle as well. Same for this one, right? You can go anywhere, like here, all right. Sorry for my terrible drawing, but for a lens, imagine if you got a lens like this. Lens is transparent, remember. You cannot set up the so-called tripod or the legs on the lens, right? But for mirror you can. For mirror it's fine, because we don't care, right? This is the other side is not transparent anyway, so it's up to you wherever you like to set up. So that's why for lens you can only set the support along the rim only. All right, here this sentence is saying the mirror can set along the rim and the back, but for lens you can only set along the rim only. All right, oh, actually it's here. Okay, rim only for normal lens. So that's why it's much harder to arrange in terms of its own weight. All right, for refracting telescope. So that's why for building a big one, you need to use a reflecting telescope usually. The other good thing that we also talked about in the previous subchapter is about aberration. So we talk about chromatic aberration. If you forgot what that is, try to refer to my previous video. And that is something to do with when light's going into the glass, because of different refractive index for different color or different frequency, then they will have chromatic aberration. That means they have different focal length. And because of for mirror, the light when they go in, I mean, they just simply get reflected on the surface. If this is a mirror, all right, and so there would not be any chromatic aberration. So that would be a very good point to improve the image. And this one, yeah, basically it's like what I said. Okay, so that's why for the largest telescope, they are always reflecting. Okay, the other thing that between Newtonian and Cassegrain, actually this picture I found on Google. I think it's better if you if you don't say this is reflector, because both of these are reflector, you rather say this is Newtonian kind of telescope. You can see that the Cassegrain, because of its design, is somehow shorter comparing to the Newtonian. So in the, should I say industry, or maybe I should say those like people who are having such hobby, it's actually quite controversial, like to use, some people may like to use Newtonian, some people may like to use Cassegrain, because both of these got its own advantages. So there's no like definite win. But comparing to refractor or refracting telescope, people don't quite like to use it if you are like call yourself and like having such a hobby for stargazing. So usually you have a reflecting telescope. Here is a summary which you can find on the Chromatic. So you see that they said the primary mirror, the first mirror that you go with, is a parabolic. Actually it should be parabolic always. And is it really concave? Let me double check that. This is concave, yeah, and this is concave as well. Yes, both of these are concave, but this one is actually convex, right? The secondary lens is convex, so be careful with that. So it said the secondary mirror is actually a convex mirror. Okay, so this is a bit different for Cassegrain telescope. For Newtonian, it's just simply a flat mirror. In fact, Newtonian is earlier than Cassegrain. All right, it's basically the first, apparently invented by Isaac Newton. The first reflecting telescope. Okay, of course, if we talk about history, then refracting telescope is the first one. If you pay attention to my comment on YouTube, last time I told you that Galileo is the first one built the refracting telescope, and then Newton is the one who first built the reflecting telescope. So yeah, I don't know whether this is important. I think it's all right. And this one I mentioned it for Newtonian. You see at the side, Cassegrain you see at the back, and the length is usually more compact for Cassegrain. Okay. Actually, from my experience, IB, I don't feel they ask you in that detail for these two kind of telescope. But I think it's good to know about the basic design, and as long as you understand, I think the most important is understand the ray diagram, then it should be fine. And actually understanding this is just simply relying on what you have learned about lens and mirror in the previous chapter. Let's talk about the next one, single dish radial telescope. So like I showed you in the video, this is actually a telescope. All right, it's not like a special building or whatsoever. But of course, this telescope is not looking at visible light, right? Because what we just showed you here, all these three kinds are looking at visible light. We are observing stars, we are observing the moon, etc. And for this one, is usually observing for something that is even harder to observe, which apparently this is called radial telescope. So of course are receiving radio wave. The only equation that you require is here. Let me zoom in. The angle is referring to the resolving angle. Guess what? You have learned it in chapter 9, I think, wave. And if you try to look at this equation and try to find it from the data booklet, can you see anywhere? You cannot see it anywhere because it's not on the data booklet on this page. However, you can actually find it. So this is exam tips. You can find it, as I said, you learn it in chapter 9. So right here, 9.4 resolution here. All right, you have learned the right line criterion for resolving the two lights or two light source. So I'm not going to explain how we can get this equation again. And whenever you see question regarding the radio telescope for calculation, just simply recall this equation. There isn't much you can do. It should be usually quite simple. Okay, trust me. So if you try to look at and try to understand this equation, then you will find out The reason why we want to build such a big so-called telescope is B is referring to the diameter. Alright, like this is B. You may want to annotate on your own taskbook. So if you try to look at this equation, if B increase, then what happened to the angle is you may say the angle would decrease. Alright, or you can imagine is if you keep the angle the same, because you know angle is maybe depending on your ability to distinguish, but then the wavelength that you can detect would also be increased in that case. So that means that you can observe for a higher frequency. It's a high frequency, actually lower frequency. That means a radio telescope, right, could be observed in that case. And normally you cannot, because it just simply cannot be resolved using the usual way with a small radio telescope. So the bigger you want to build, then the higher wavelength, that means the lower frequency you can observe. And in fact, from the outer space, there are also a lot of radio wave we can detect. And there has been many years people think that, hey, would those radio wave from the outer space sent by alien? And we still don't know. All right, if you are interested in alien, then maybe you may want to build one and try to analyze those signals and see maybe the alien are trying to communicating with us. The next one, as I said, is basically an array. Array means many, like forming a certain pattern. All right, this is an array of telescope, and the basic idea is, since we cannot build one single dish that is, I mean, the biggest you can build is probably at like this big, all right, like, or a little bit more bigger. But then the thing is, it's hard to maintain. So people thought of using mathematics, of course. What you can do is you can actually merge the data from each of these radio telescope, and then you can combine them. In fact, later on, I'll try to talk about the black hole. Maybe I should talk about it now. The black hole, if you know, the photo of black hole was taken, well, actually it's been almost a year already. This is April, you can see, right? It's 2019 April, so about 10 months already. And this is the first picture of black hole human has ever been taken, and it was a big achievement in physics and astronomy, because we have been predicting black hole for a long time, and finally we could take a picture of it. And if you never know about this, I think it's not too late still, but there's something that you should at least know as a physics student. Is, first of all, the so-called, it looks like some light, right, like red light from your screen. You can see like it's like some fires burning here. These are not visible lights. Be careful, these are not visible. That means if you try to look at black hole, it's really black. There's no light can escape. That's why we call it black hole. And these color are artificial. It's based on the radiation sent out by the black hole, and we would guess what happened actually inside this. The literally the one that is in the middle, this one is a black hole itself. These are the light that could barely escape, like the donut shape, barely escape from the black hole. If you want to understand this picture in a more detail, Veritasium has made a really nice video. I'll put the link in the description. And in his video, he used a really nice model to explain why. I mean, just now you can see the bottom of the ring, you can say, is brighter, and how come at the top is dimmer. So he made a really nice model to explain why that is. And I would say, well, of course, this is not going to be in the IB exam, but as a physics student, I would really hope you can understand it, and if someone asks you, you can explain to them. There's also another video I would like you to watch as well. Try to spend your time. I will again put the link in the description. It's about how come taking the photo of the black hole is such a big deal and how we could take it. And that is something to do with, as I said, the array of radio telescope. But of course here it's not just an array only. It's literally, you may say, the array of the whole Earth, basically. Because if you have heard about the news about how we take the video, take the photo, it's actually taken from different country. There you can see there's some radio telescope from the different part of the Earth, and then what scientists did was to combine those data by using a supercomputer. And it was very challenging because the Earth is rotating and the black hole is very far away, and there isn't much thing, like you can see this is from many countries around the world literally. And again, as I said, the Earth is rotating, so it's not easy to justify the data, and there's a lot of correction you have to do for the data that you receive. And at the end, you can try to listen and watch this video. They would take a long time. They even have to literally, the data are so huge they can't even send through internet. They have to pass the hard disk by flight going to I don't know which country to combine and process the data. And at the end they finally make such a really nice picture. You may think that, oh, this picture is like really terrible pixel, it's all pixelized, bad, very bad resolution, it's like out of focus. But then actually this is a very nice picture you can take already out of the technology that we have. So again, please try to watch this video. And actually I think this question might come up in the IB exam about the nature of science itself. How come the scientist has to work together? This is a very common question you may encounter in these events of taking a photo of black hole. So really think about and try to watch the video. Lastly, in the textbook you may also find there's, in the syllabus I should say, two kinds of telescope, and you're expected to compare them. So here is a very nice list made by Chromatic. So let's just go through it together. For Earth base, most of them, most of the EM wave are all completely absorbed by the atmosphere, except for visible light. So I think this is a reason why the Earth are suitable for us to live, because for most of the UV and most of the X-ray as well, which X-ray and UV are not good for human health. Getting too much of that, you may cause cancer apparently. So that's why we have atmosphere for us to block this, and that's why we are still surviving on Earth. But the problem with that is when we try to use telescope, then since most of these waves were absorbed already, so what can you expect? You can't observe anything or not observe the full picture. So that's why some people, actually it's more like national level, like some country literally send the telescope onto the space to make observation, and that is in that case then you don't have to worry about the atmosphere. You can really observe the really raw data and the full EM spectrum. And in case you are curious, I also put this link. Actually you can search it easily on Wikipedia, and this is a really nice summary of the space telescope that by sorting by different electromagnetic spectrum. So let's take a look very quickly. So here we got gamma ray space telescope, and you can see there are lots, right? Some of them are retired, should I say retired. Some of them are active, as you can see, and I think most of them are from USA, NASA, you can see. And you can also see X-ray. So you can see that for different space telescope they need different, they really get one telescope for a specific EM wave. right? Because that will require different size, different designs as well. UV, you can see there's a few as well, actually a lot. Visible light, okay, and infrared, also quite a lot. Microwave, not a lot, but we also got 4. Yeah, Swedish. Radio and even particle as well. All right, or some of them I think appear in the previous, so maybe some of them can do multiple detection. Okay, and I think one, yes, here this is a very special one, gravitational waves. So this is the one that I think 2-3 years ago, the reason how people said the Einstein gravitational waves theory has been proven, and that actually with the help of this satellite as well. Back to our list here, we also would consider the light pollution, as you all have experienced if you went to the camp, when the light is too bright, or even if the moon came out, because the moon is actually very bright comparing to other stars in the sky. That will cause light pollution basically, and that will affect the observation. Right, you simply can't observe; it's too bright. And for satellite, of course, is not going to be suffer. In terms of atmosphere, because of the atmosphere, of course, there are so many activity in the atmosphere. You know, the aircraft are flying, the flow of the air movement, typhoon, etc. Affect so much, and this is why the telescope are often built in the mountain. If you remember last time, the guy who organizes the camp, he mentioned that his company built a lot of telescope, and you will find most of them are in the mountain, and that's because you want to get closer to the sky, and there's less disturbance. And of course, for again satellite is not going to be affected. For the cost, apparently on the ground is much cheaper. For satellite, the building cost is expensive, and launching it will be expensive too, and you can easily get a risk of failing. I mean, you can launch a satellite but it fail, so it's a big investment. That's why it will be national standard usually. Like it's much harder to build it by yourself. For maintenance, it's easy to maintain if it's on the ground apparently. But then of course it will also able to be damaged by the turbulence of the atmosphere. For the space one, however, the other issue is you don't have much thing in the space, but you have to think about the temperature change, because the sunlight really shines on you without any air layer, so the UV infrared got directly onto the machine, and that's why you usually see they are very shiny, because they want to reflect those infrared or UV away from the machine. Of course, the thing that they want to detect will go in from the middle, going to like the scope inside. But then for the other side, they don't want it, so usually it's shiny. Operating time, of course, for the Earth one, you can only do it at night. You can't observe stars in the daytime. For space one, it will be 24 hours. Okay, so that's actually pretty much for this chapter. To end this, there's a question I want you to do. Please pause the video now and come back to us for the answer. Okay, so here's the answer. The first question is actually asking you what it means by radio interferometry. That means it's an array. So I think the most important word that you want to put down is array of radio telescope, etc. And for part B, it's simply using this equation, as I said. So this is the angle for minimum observing angle, and so you just substitute everything inside. Just be careful, this is cm, this is km, so divide 100 and times 1000. You'll find the answer in radian, and that is simply the answer. For part C, I think the best approach is to draw a diagram. If you don't know what it means by the question itself, draw a diagram like what I did. So here is the observer on the left hand side. Here is a galaxy. So it said the smallest separation that can be resolved, right? So that means the smallest separation I use S to represent that you could resolve. You can see two distinct sources. And the distance, that much from Earth, so that will be the distance. All right, 2 times 10 to the power of 22 meter. And for calculation, it's actually very simple. After you draw this, it's very simple because you know the angle is the one that you find in part B, and then that angle would equal to S over the distance here. All right, if you don't understand how come I can get this equation mathematically, go back to study the previous video. I talked about we have to use small angle approximation. We can try to use theta divided by 2 and then use the tangent theta over 2 to and small angle approximation to do, and at the end of the day you would have the same equation as this one here. Okay, and then you can proceed on, just simple algebra. You find out S will be that much. Okay, so that will simply be the answer. And that's all for this C2 for option C.